Now you're watching the educational channel YouTube. Today we are going to start talking about the alkenes and cycloalkanes, and this is the first video to introduce the hydrocarbons. Hydrocarbon is the simplest organic compound that is made up of carbons and hydrogens only, and the carbon-carbon bond provides the scaffold of the framework, and when functional groups attach to the carbon-carbon bond that we have, it makes the organic compound more complicated. Hydrocarbons are divided into big two classes. The big it is aliphatic, and the other one is aromatic. Aliphatics are simply made up of three major groups. They are alkenes, alkanes, alkenes, and alkynes. Aromatic has another name, and it is sometimes called arenes. So examples for alkane could be an ethane, and ethane is made up of 2 carbons and 6 hydrogens. And example for alkene, we shall talk about ethylene and double bond with 4 hydrogen. And an example of alkyne, we can talk about acetylene, and acetylene has triple bond between carbons and 2 hydrogens attached to it. An example for aromatic, we can talk about benzene. And benzene is made up of 6 carbons and double bond, single bond alternatively. And at the single bond, or there will be 6 hydrogens attached to each carbon, and this compound is named benzene. Talking about electron waves and chemical bonds, here's a graph that introduces the hydrogen bonds, or the bonds between 2 hydrogen atoms. So the y-axis will be our potential energy, and the x-axis will be the internuclear distance between 2 hydrogen atoms. 74 picometer will be the ideal where the hydrogen bonds are usually found. The length of the hydrogen bonds are usually found. And in here you see the potential energy is the lowest, and we say this is the most stable part. And potential energy here is approximately negative 435 kilojoules per mole. And as the internuclear distance gets larger, we follow the graph. And when it's too large that 2 hydrogen atoms do not form the bond anymore, we will see the radicals of 2 hydrogens, and the potential energy between 2 hydrogen bonds is almost 0. And we use the 2 widely used theories for chemical bonding to set up this graph. One is called the valence bond model. And the other one is molecular orbital model. So, as the distance between two hydrogens decreases, the forces involved so the forces will be the negative and negative between two electrons from the hydrogen, and positive and positive between the nucleus between two hydrogen, also the negatives and positive from the alternative electron and nucleus attractions. The forces involved will always increase. And that is the reason why after certain moment the potential energy increases exponentially. Talking about the bonding in hydrogen molecule, the valence bond model. So in drawing A, we see 1s orbitals in each hydrogen that they're not overlapping at all, and as the hydrogen nucleus approach, or nuclei approaches to each other, they start forming these interactions between the electron shells, and they start begin to overlap. And in the third picture, C, the bond in which the overlap or the orbitals overlap along a line connecting will be now called, or this region right here, by the way, the length between, or the distance between the two nuclei will be approximately 74 picometer, and the new region where we say the electron density is the greatest, we call them the sigma bond, and we use the letter that. Introductions to alkanes: methane, ethane, and propane. Alkanes have a general formula, molecular formula of CnH2n plus 2. So as an example, if n is equal to 1, CH2 plus 2, which will be 4, n is equal to 2, CH4 plus 2, which will be C2H6. Indeed, this is methane, this is ethane, and 1n is equal to 3, C3H8, this is propane. The boiling points of those will be negative 160 degrees Celsius, negative 89 degrees Celsius, and negative 42 degrees Celsius. So the pattern is it increases as number of carbons increases. So the bigger carbons, like when n is equal to 70, it has a name of heptacone. It has a boiling point of 653 degrees Celsius. Instead of having an s orbital and also p orbital, CH4 has a special new type of orbital called hybrid orbital, and especially CH4 has a hybrid orbital named sp3 orbital, and this is a combination of 4 electron bondings, 1 from S and 3 from P shell that looks like you have a carbon in the middle, and has where S shell has a circular shape and P shells has, when this is X direction, Y direction, and Z direction as an example, has a shape looking like this. The sp3 hybrid orbital has a shape looking like one going up, one going to the right, and one comes out, and last one going to the back, like that. I think it would have been more clear if I tried, like, let's say this is a hydrogen atom, and this is a carbon atom, and here's another hydrogen atom, a third hydrogen, and a final hydrogen. That's a combination of s orbital and p orbital, and we name it sp3 hybrid orbital. So if you think about having the carbon in a plane, so let's say the plane is vertical, then this hydrogen is on the plane or in the plane, where this hydrogen is coming out from the plane and that hydrogen is going also away from the plane, and this hydrogen is also on the plane, in the plane. And here let's talk about bondings in ethane. So ethane has one carbon and another carbon connected, and it has one hydrogen, another hydrogen, one hydrogen going out this way, the other one going that way, this way, going that way. And we call that CH3 from the left side or the CH3 from the right side. Each group will be called methyl because they are very similar to CH4, which is methane. So when CH3 is there as a subgroup, we call them methyl. So ethane C2H6 is made up of 2 methyl groups, and they both have sp3 and sp3 hybridized carbon attached. In sp3 hybridization, 4 atoms are attached to a carbon by the pi bonds. There will be, if this is a carbon, there will be group A, or let's use X, Y, Z, and W, they all attached to the carbon by pi or sigma bonds. But in a case of ethylene like C2H4, where there is a double bond between two carbons and two hydrogen, the bonds labeled with the yellow shall be considered as the sigma bond that is made up of sp2 hybrid orbitals, where the bond in blue shall be considered as a pi bond, and the pi bond is from an unhybridized orbital of p shell. And because now two carbons are connected with double bonds, they are shorter in distance than ethane. So let's compare the three basic models of the alkanes. CH3, ethane had sp3 hybrid orbital, and the length between two carbon atoms was 153 pm, and the length between carbon and one of the hydrogen will be 111 p. And C double bond C with two H's, and this molecule is named ethylene. It has sp2 hybrid orbital and one unshared p orbital. That p orbital has pi bond. The distance between two carbons is 134 picometer, which is shorter than 153 picometer. And the distance between the carbon and hydrogen is 110 picometer, where there is not much of the difference with ethane. And lastly, the triple bond. This molecule is named acetylene. Has sp hybrid orbital with p2 orbital of 2 pi bonds. So we can see two unshared electron pairs here, and the distance between two carbons is 120 picometer, where distance between carbon and hydrogen is 106 picometer. And I'm labeling also the blue bonds shall represent the pi bonds, and the black ones are the sigma bonds. Let's do one example, a molecule named vinylacetylene. It has one double bond and another triple bond right there, and the problem says identify the orbital involved in the indicated bond. So here this is the indicated bond, and it will be easier if I draw out this hydrogen upward. So every atoms or molecules that are connected with a single bond, then we can say these are from the hybridized orbital of sp3 if there is no double or triple bond, sp2 if there is a double bond, and sp if there is a triple bond. So in the point of view of this carbon 2, it has one pi bond from the double bond, so it's sp2 plus one p orbital from the pi bond. And in the point of view of carbon 3, actually I should have named it, numbered it 2 and 3 alternatively, has two pi bonds, so it is from sp hybridized orbital. So we can name the indicated bond as sp2 sp sigma bond. How many pi or sigma bonds are in the molecule? The simplest way to count the number of sigma bonds is you simply count how many atoms there are and how many lines there are to connect them. So this carbon, let's draw out the structure of this carbon. So I'm going to have 1 or 2 H's, and this one may have an H right there too. So there's a connection, and I meant the connection to represent the number of sigma bonds. So it has 1, 2, 3, 4, 5, 6, 7 sigma bonds, and 1, 2, 3 pi bonds total.